Welcome to this lecture on VHDL in the course Digital System Design with PLDs and FPGAs. The last lecture we have gone through the use of multiple architectures, two models of description. One is data flow model and the behavioral model. So let us look at the slide. When you have the multiple architecture for a single entity, it can be used, you can have a scenario where you write a quick code for simulation, or another architecture which is kind of after the simulation you can do it for synthesis. Maybe you write one architecture for minimum area and the one for maximum speed, one could be for FPGA, one could be for PLD or ASIC and so on. And we have seen the design flow. We start with the VHDL source code, which is functionally simulated. The code is simulated, not the circuit, to remove the logical and syntax errors and iterate here. Then you go for synthesis where the logic circuit is created and you can do a logic simulation. If you correctly code, if you correctly write the synthesizable code, this step may not be necessary. So you can do a logic simulation, which is both these simulations have no delay because it is not mapped to the device set. Then once you do the synthesis, you can go for the process of place and route or fitting. Place and route is called PAR, and you give IO constraints and timing constraints, do quick static timing analysis depending on the delay of the block, and when you iterate there and when everything is okay, you do timing simulation, which might take time for complex circuits. Then everything works fine, then you can program the FPGA. So basically you have an editor, you have a synthesis tool, constraint editor, a PAR tool, a programmer, a static timing analysis tool and a simulator which does all these functional, logic or timing simulation. So these are the kind of the tools we use, and we have seen the data flow model. The first code as an example we have seen is a data flow model where it shows the data flow. This is the input and the output gets assigned, and this uses a construct called when-else statement which is used in the concurrent body. So this is a concurrent body. Everything in the architecture statement region is concurrent, and this is a concurrent statement. There is another statement called with select which we will see later. There is another way of writing using the logical kind of operators. As I said, this can be cumbersome when the data size is large, and so here even if whether it is 3 or 31 it does not matter, this works. So this is very concise, you need not worry about the circuit you end up with. These are very simple thing to synthesize. So the synthesis tool will make sure that whatever you have written the equivalent circuit depending on the device in an optimal way is implemented. So that is the data flow model, and we have talked about the concurrency. As I said, there is an issue, like it is not like unlike the sequential languages. When you write some statements in a specific order, in a sequential language one after the other is executed, but when you basically simulate a VHDL statement sequentially written concurrent statement like this, a top to bottom evaluation will not yield the correct results. So the simulator has to resolve concurrency from the sequentially written code, because here it is written in the opposite of the data flow. Data flow is from AB to X, X to Y, Y to Z. We have written in the opposite way, so Z and Y will be wrong, X will be the correct thing if you do the top to bottom evaluation. The simulator's job is to resolve the concurrency from the sequentially written code, but it is not a big issue for the synthesis tool, because the expressions are there, and whichever order it is written does not matter, you end up with the same circuit. So in this case, at least for in this case, the simulators has a hard job than the synthesis tool. We have looked at the behavioral model where we use everything else is same, where we use a sequential body called process, and process as a sensitivity list. We put the inputs there. When anything changes in the input, it computes from top to bottom once, and it uses sequential statement like if then, case when and all that. And before the begin you can declare the variables, you can declare constants, you can define procedures or function which are visible to the body. You have a problem if you miss something in the sensitivity list, because here you see in the statement there are two inputs, but if you don't write both inputs then the simulator will give a behavior which the synthesis tool won't be able to kind of produce, because synthesis tool doesn't bother about the real time behavior. It looks at the code and generate the circuit. Code say if A is equal to B equals get 1, else equals get 0. So it just create an equality comparator, but the simulator simulates an equality comparator which works only when A changes. If B changes, next time A changes it works correctly if B doesn't change till the A changes. Otherwise if the B changes it doesn't compare, something like that. So there is a problem, a compatibility problem with the simulation and synthesis. The solution is to write all the input signal in the sensitivity list, and some tools warn you, and if the tool doesn't warn you it's a dangerous thing, because you simulate and see some behavior, and this in a complex case sometime it can be, in very simple case you will be able to identify, but in a complex case it can create an issue. So one need to take care of this particular issue of missing signals in the sensitivity list. And as I said, there is nothing great about using processes. Don't get kind of worried about this word processes. If you have a block with inputs ABC, you write ABC in the sensitivity list, you use if, case, loops etc. to define the behavior of this output in terms of ABC. That is all what is required. As I said, when I say write the input signal in the sensitivity list, little more detail is required. Maybe today's lecture will throw light on it and we will go ahead. And we also said when you have multiple processes, both are concurrent, say you have two blocks, they share an input called A, so you write two processes, and if A changes both will be computed for the same event. Okay, it's not that the simulator cannot compute at the same time, need not be, but if A changes at 100 nanosecond, both these computation will happen for that particular 100 nanosecond event. That is the meaning of concurrency. So let us go ahead and let us come to today's part, and here we see a model of description called structural model of the VHDL code, which enables us to do the hierarchical design or the top down design. And we have seen already how we have designed the CPU top down. We put a black box CPU, say level 1, where it was an interconnection of various components. So we will see how that can be done in VHDL using the structural code. That is the basic idea. So when you have a top level entity which is built up of the black boxes from the level 2 or the bottom level components, then what is done is that the top level entity you give a name, as usual you define the inputs and outputs. Okay. Now the game is that we are not going to describe the behavior of the circuit, but we are going to say this entity, the architecture of this entity is composed of the interconnection of various components. That is what is going to be stated in the architecture statement region, and for that we need to say what are the components used. Okay, so maybe you take these two components, they may be same components. Okay, you can have a same component instantiated multiple times in an architecture. So you have to declare in the architecture declaration region before the begin the component name, its inputs, its outputs and the data type, exactly like the entity of that component has to be repeated. The idea is that you are going to put another component and you are going to connect using some signal, and you know that the VHDL is a strict data type checking language. So if you are connecting an output to an input, if output is of the type standard logic, then input also has to be standard logic, and this wire or the signal connecting them should be of standard logic. So we have to declare the distinct components we are using in the for the interconnection in the architecture declaration region, all of them, and we also have to, you see this signal, this is not part of the input or output. So we have to declare that signal, it is called signal which has no direction, because signal connects some output to input, one or two inputs, one output to one or two inputs normally, unless you use a tri-state gate. So the signal does not have a direction, but it has a data type and everything has to match, okay. So the game is you define a top level entity with input output port. In the architecture declaration region you declare the components, essentially its name, ports, direction, data type, everything, various components, and what are the internal signal you are going to use, that has to be declared, because that is not part of the input or output, that has to be declared. What is the name, what is the data type, and when you come to architecture statement region you say how these components are interconnected using this signal, or you can say we define the netlist of this interconnection, okay. We say the component 1 particular output is connected to the component 2 particular input using the description language, that is the basic idea. So to make it clear, let us take an example, we will take the same example, okay. We will take the equality comparator we have described using the data flow model and the behavioral model. So we will use the same thing, and you know it is a 4-bit equality comparator. So it needs to check the equality of all the pair of 4 bits, A3 equal to B3, A2 equal to B2, A1, A0, B0 and so on, okay. So this equality is checked by exclusive NOR gates, and the output is going to an AND gate. If all are 1, the output is 1, okay. So we have 2 distinct components, we have a 2 input exclusive NOR gate and 4 input AND gate, okay. Now we have only 2 components, but this particular 2 input exclusive NOR gate is instantiated 4 times, but we need to declare only once. And AND gate, similarly we have a 4 input AND gate which is declared once, instantiated once, but mind you we have some signals which is connecting the output of XNOR gate to the input of AND gate. So these are internal signal, this need to be declared, okay. So we have 4 signals, this 1, 2, 3, 4 that need to be declared. So we are going to give a top level entity of the equality comparator. In the architecture declaration region we are going to declare a component exclusive NOR and AND gate, we are going to declare 4 signals, and in the architecture statement region we are going to show this this component will be instantiated 4 times, this 1 time, and we will show the connections of the wire connection. That means we will say A3 is connected to the first exclusive NOR gate first input, B3 is connected to the second input of the first exclusive NOR gate, the first exclusive NOR gate output is connected to the first input of the AND gate and so on, okay. We will see how that is done. So let us go to the VHDL code. You see the entity part is exactly same. We have the library declaration, the package use statement, entity, exactly similar to the previous one. A and B are 4-bit vector, equal is a single bit vector. Okay. When it comes to the architecture part, you see before the begin there is an architecture declaration, and there we are going to declare components and the signals. And you see the component, this component is XNOR 2 XNOR gate, this one, and the port is I1 I2 in standard logic, 2 inputs of type standard logic, O1 colon out standard logic, 1 output which is standard logic. And you see normally in architecture entity there is an is syntax, but for some reason VHDL does not have component name is, there is missing, so do not write is, it will give an error. And here the AND gate is declared, so component AND 4 which has 4 inputs and 1 output. So the port I1 I2 I3 I4 in standard logic, O1 is out standard logic. So normally when you write the description of the AND gate and the XNOR gate, this component declaration is exactly like the entity. So it is enough if you write the component entity and architecture, you copy paste the entity here, change the entity and end to the entity to the component and this entity name to the component and remove the is, then you will get it. And this is similar to in a C code when you write a C language program and use a function, if the function is elsewhere then you write a function prototype. Okay, many a times that you will find in the header file, which then checks for the type of argument passed and all that. This is something similar because VHDL is a strict data type checking language. So ultimately we are going to instantiate this component and connect some wires to it. So the tool will check whatever the wires you are connecting is of the same data type. So that need to be here, that is why this component part is here. We will see how to write a component in the library and use it and so on, but the basic purpose is that. And this component need not be as part of this particular the file, it can be elsewhere, it can be in a library or it can be elsewhere, it does not matter. Now before we declare the signal, the syntax is signal, name and the data type. So we have 4 signals which are of the same type, we use the we specify in the same statement signal int1 int2 int3 int4 colon standard logic. Okay, that means that we are naming this as int1 int2 int3 and int4, that is a game. So we have declared the 2 components, we have declared the signals. Now we are going to instantiate this 4 times, instantiate this 1 time and going to interconnect them. That is what is going to be done. So this is what is shown here. We connect A3 B3 to the first one, the output is int1, A2 B2 int2, A1 B1 int3, A0 B0 int4, and the AND gate get this int1 int2 int3 int4 and the equals. So the syntax is simple, you give a label, some label does not matter, colon the component name, and we say the port map, that means the actual formal ports which we declared as I1 and I2 is mapped to the actual port. So we are going to specify a formal to actual mapping, that is why it is called port map, and we say A of 3, B of 3 and int1 because we have declared this as I1, I2 and O1 in the same position. So we are associating A3, B3 and int1, that is this one. Similarly C2 XNOR 2 port map A2 B2 int2, A1 B1 int3, that is this, A0 B0 int4, that is this one, and ultimately this AND gate which gets int1 int2 int3 int4 and equals int1 int2 int3 int4 equals in the same order. Okay. So this is called a formal to actual mapping by position, or we can say we are associating the actual to the formal in a positional way. So it is called positional association. So you have to remember the order, like that the AND gate inputs can be in any order, but then at least you should remember where the input is, where the output is. Suppose if we had specified in the declaration equals at the beginning, then we have to bring the equals here so if the O1 was at the beginning, then equals has to be written at the beginning. So this is kind of done. This is how the structural description happens. Instantiate the components and formal signals are mapped to the actual signal by position. It is very simple, there is nothing great about it, and but ultimately now we say that this can come from a library or it can come from a different file. Ultimately there has to be description of the XNOR gate and the AND gate for it to happen. It may be in the library already compiled, it may be in the project in another file, but it has to be written sometimes by somebody. Okay. So I am, for completion sake, I am showing that. So we have the component XNOR2 library close entity port I1 I2 and O1, and the architecture we have very simple statement, O1 gets I1 XNOR I2, and that is the end of the architecture. Similarly you have an AND gate which is 4 input I1 I2 I3 I4 in standard logic, O1 is out standard logic. In the architecture declaration statement region we have O1 gets I1 and I2 and I3 and I4. So it's simple as it is. So if you write this and you compile it, this will be same as the behavioral code or the data flow model and so on. At this point somebody might ask, is there a difference between the earlier code and this code which gives a better circuit? At least for the simple very simple cases like this it does not matter at all, but when you write a very complex circuit using behavioral, the data flow and the structural code, you can get different circuit. It depends how you understand, how you describe and things like that. So we cannot say, but if you follow the strict practices what I am going to teach you, then you can be sure that you will get the kind of the expected circuit with maybe some kind of optimization in all 3 cases. You need not worry, at least in simple case you can close your eyes and choose. There is no need to, frankly, if you are making an equality comparator, there is absolutely no need to write a structural code just to illustrate, because if I take an example, complex example, it runs into pages, and just to illustrate I have used a very simple code, but you do not do that. There is no point in making a ripple adder or a equality comparator using a structural code. When you have complex design which is partitioned into multiple pieces, then those partitions are combined in a structural code, top level or the level, second level and so on. But when you come down you can still use the behavioral and the data flow description when you really describe the known high level functions as we discussed, like mux, demux, encoder, decoder, adder, subtractor, all that can be described behaviorally or in a data flow model, and when we come up, when you put it together, use a structural coding, that will be easy to kind of keep track of. Then again you can combine them in a behavioral way, but then it can be complicated to track. It is easy to use a structural coding at the top level when you connect the complex blocks together. Okay. So let us move on, let us see some kind of let us look at this component instantiation. The way we have done the positional association is like XNOR2 port map then I1 is mapped to A3, I2 is mapped to B3 and O1 is mapped to int1, positional association. But when you, this is okay if you are writing the code and the code is in the same file. Suppose you have written the X02 code that is in the same file, you can scroll down and check the order of the formal ports, then you can map it correctly. But when somebody has written a library component in a library, it is very difficult to keep track of the order, but they can give an input output table where the input signal name and the data type is described and the function is described. So it will be convenient if we can forget about the order of the ports. We can say what is the formal port name and what is the actual port name. Association can be specified explicitly, that is called named association, which is the most useful way of doing the port map. So that is like this, you can say for the previous case, this case you can say X02 port map, O1 is mapped to int1, I2 is mapped to B3, I1 is mapped to A3, exactly similar to this. You do not have to keep any order, you correctly say which formal port is mapped to which actual part, that is it, okay. So that is the named association, the most useful way of describing the component instantiation. So let us move on. You know that when you write some software code, like if you are a computer science student or you have written some serious software, one important thing before you write the code is the data structure, okay. So algorithm, you have the proper data structure if you define, then the code will be very easy. You can have an elegant the C code if the data structure is correct, where you are supposed to use an array. If you use a kind of distinct variables, set of distinct variables, the code will be very clumsy. So similar to that in VHDL, if you define the signals in a proper way, the code can be very elegant and concise. So I am going to show the same structural code we have written. I will introduce a slight change and show you how it can simplify the code, how it can make elegant, make the code elegant. So let us move on. So we have declared earlier the internal signals as 4 distinct signals called int1, int2, int3 and int4, okay. You remember that. Suppose instead of that I am going to declare this signal as a 4-bit vector, okay, or 4-bit array or whatever, 4-bit bus, okay. So I am not calling int1, int2, int3, int4, so I am calling the signal int, okay, which is standard logic vector 3 down to 0. That means you have an int of 3, int of 2, int of 1 and int of 0. The moment I write like that, then what I do is that earlier code was written like this, A3, B3 and int1. So I could write now, instead of that I have changed the declaration to a bus which is 4-bit. Now I am going to change the description which say X02 port map A of 3, B of 3 and int of 3, A2, B2, int 2, A1, B1, int 1, A0, B0, int 0. In the 4 the component instantiation or the XNOR gates, and in the AND gate the inputs are int 3, int 2, int 1, int 0 in any order and the equals, okay. Now you see here this comes neatly, you have 3, 3, 3, 2, 2, 2. So you can write something called, for this 4 statements you can write a loop called generate loop. So that is written shown here, for I in 0 to 3 generate C X02 port map A of I, B of I, int of I. That means it goes from A0, B0, int of 0, A1, B1, int 1, A2, B2, int 2, A3, B3, int 3. You might ask what happened to the label. We are not giving C of I, you don't need to give, you just give C, you will automatically get C0, C1, C2, C3, okay. Don't worry about the label, and ultimately you have to write the instantiation of the AND gate. Now mind you, this is not a loop in a conventional sense of the sequential language, because in a sequential language something is kind of executed one after the other, but this is just a short form of writing it explicitly. When the compiler tool see this, it will replicate it 4 times, like A0, B0, In0 up to A3, B3. So it's a very concise way of generating this statement. So if you take care when you write the code, when you have something replicated with some symmetry, it has to be symmetrical, and a proper definition of the signal can help you in getting a very simple concise code, and which is easy to kind of understand. Otherwise you have to, suppose you have something replicated 12 times, then you have this issue, okay. So you can think of doing this for, suppose you have a ripple adder where the full adder is replicated 8 times, you can write a generate loop. You might need to define the signal, the carry input and carry output, that need to be taken care, but that can be easily taken care. So that is one example of this generate loop. You can definitely write a generate loop for an 8-bit ripple adder using the component as a full adder, but suppose if you use a carry lookup adder, that is going to be little tough, because in a carry lookup adder is not symmetric. When you move from 0 to 7, it becomes exponentially bigger, and you can do that, you can write a loop, but probably not a generate loop. Maybe we will see what to be done when you go ahead. And one more thing about instantiation, when suppose you are instantiating a component and one of the output is not connected, okay, then when you instantiate, suppose see we are using a 4 input AND gate, or you say equality comparator with 3 output, one is equal to, one is greater than, one is less than, and we are using only equal to in the instantiation. Then when you come to the greater output and less output, when you instantiate you have to say, since it is not used, you have to say open. And similarly if some inputs are like you are using in some case you are using only the 3 inputs of an AND gate, then one of the input has to be tied to 0, the inactive level, depending on whether the function is AND or, okay. So you have to properly tie it to the appropriate logic levels when an input is not used, otherwise things won't work because we are describing the hardware, so that need to be taken care. So let us, so that is about the different models of description. The structural coding is what we have looked at. Basically we instantiate, we declare components, declare internal signal, instantiate it, and interconnect them by describing the interconnection using the internal signals and ports. And if you elegantly define signals, you can use the kind of concise elegant generate loops for a kind of when there is quite a good symmetry, you can work it out, it becomes concise. And if an output is not used, you have to say open. Input is not used, then you have to pull it up or pull it down depending on the function of the circuit to make it inactive. So let us move on now. That is the 3 different models of description. Now let us look at the simulation, okay. I don't know whether you have done any digital simulation. Maybe in your the undergraduate you have done the analog simulation using SPICE, and so in a SPICE simulation, suppose you have a system, maybe a filter, let us take an example of a low pass filter, and you give some input, say maybe some trapezoid waveform, and you will definitely the low pass filter, depending on the cutoff frequency, is going to smooth it out. You will get a triangle wave or sine wave depending on how the filter is designed. But in a, you know that in a SPICE simulation it is going to divide the whole period into minute intervals. Okay, it need not be uniform because you know in a trapezoidal waveform maximum information is in this kind of slope. All the harmonics, the frequency content comes because of this kind of rate of change. So there will be lot of division, lot of steps there. When it is stable, maybe less steps. So the SPICE is going to divide it into interval, and there will be computation of the input with the system transfer function to generate the output. Okay, so that is how the analog simulation or the SPICE simulation is done. So let us see how it is different for a digital circuit. Okay, now look at a digital circuit. So you see here I have shown some, like you can imagine this is a digital system now, and we are giving some input to the system. Okay, now you see here this input is changing like that, and this one is changing like this. Okay, now suppose initially at the first step the simulator take these values 0 and 1 and compute the output, but you know the moment it is computed there is no point in dividing this into minute intervals and compute it, because it is going to be stable, because the digital system is binary. But here you see when an analog signal changes, the value moves from, all the values are important. It may be going from maybe 0 to plus 15 volt, each voltage is important, but in our case either 0 then 1. So there is no need to compute. Once 0 1 is computed, the next computation need to happen only here, because the input signal is changed from 0 to 1. So now you compute here at this point 1 1. The moment you compute, till any change happens there is no need to compute, because it is going to remain stationary. So as far as digital circuit is digital simulation is concerned, whenever there is a change in the input, at that point the simulator need to compute. Okay, that means whenever we say whenever there is an event on any of the signal, at that time the computation should happen. Okay, so in digital simulation is an event driven simulation. Whenever there is an event on any of the signal, then the simulator has to compute, otherwise nothing to do. Okay, so events trigger the computation, and events can be on the inputs. Maybe event happens like you give the inputs to various input signal, then you have to compute, but because of the input something can change internally, at that time also that should trigger a computation. So in digital circuit, unlike the analog circuit, we use event driven simulation. Like you take a combination circuit, then we have to simulate by you know it is an event driven simulation. But let us come to the sequential circuit. Now when you have a sequential circuit, suppose the input is changing quite a bit. Suppose we give a clock which is say of frequency say 100 megahertz, then the duration is 10 nanosecond. But maybe all the inputs coming to this register, say we have a register, combination circuit and a register. Here the input is changing say every 1 nanosecond, but we know that this flip flop is going to be latched every 10 nanosecond. So there is no point in computing the simulator to compute every 1 nanosecond. Okay, so in principle for a sequential circuit you can compute on the active clock edge and you can get the value, and that is called cycle based simulation. Every clock cycle, active clock edge, you can do the computation. Definitely you will miss a lot of things because of maybe that there could be a lot of changes happening here, and unless that is all computed the in between things can be lost. But then this is a very quick way of simulating. You do not simulate every time the input changes, when the clock comes just before the kind of that whatever is the stable input, that time only you need to compute. But you might not be able to estimate the power dissipation and things like that in the simulation, or something will be missing, but does not matter for sequential circuit because updation happens only on the clock edge. So the cycle based simulation can be used in sequential circuit. So that is a different type of simulation, and in simulation there is a notion or a terminology we use, simulation time. Okay. Now you should have some clarity on that. First of all, it is not real time. Okay. It is not that it is the time of the day or some kind of clock which is running which indicates the real time. Okay. That is not the simulation time. So real time is not simulation time. It is not even the time taken by the simulator to compute something. Say you have given a complex circuit for timing simulation, it takes 3 hours to simulate whatever you have given. That is not the time taken by the simulator, is not the simulation time. Simulation time basically is the time at which the events happen. Okay. So when you say at 100 nanosecond an event an input A changes, then we say the simulation time is 100 nanosecond. Okay. Then the simulator will start some computation which might take any amount of time, like at 100 nanosecond an event happens and simulator computes, maybe it will compute in few nanosecond or microsecond or millisecond or hours or day, it does not matter. It might take a day for the computation of the 100 nanosecond event if the circuit is complex. Okay. Now after the day everything is done, if the next event in the queue is 200 nanosecond, the simulation time now goes from 100 nanosecond to 200 nanosecond. Okay. As far as the digital simulation is concerned, because it is event based, the next event in the queue in the order is 200 nanosecond, the simulation time goes from 100 nanosecond to the 200 nanosecond. So that is the simulation time, do not confuse. Now I am giving a very kind of lucid explanation for you to understand the concept. I am not going to be very precise, I am going to avoid all the terminologies. You can go back to some textbook, there are a lot of the names, the terminology which is used with regard to simulation. I am avoiding everything. You can refer to the reference book and learn all that, but it could be confusing for a beginner to go through that. I am telling you the crux of the matter in a very lucid way. So I cannot be very kind of precise, but I am trying to explain the concept in a clear way. Hopefully you can understand. And very important is that events are ordered in the chronological order or in the simulation time. What I mean is that suppose you are trying to simulate a circuit and you have given say you have an AND gate you are trying to simulate and 2 inputs are there. Say you give some waveform which changes at 100 nanosecond, 200 nanosecond, 250 nanosecond and 300 nanosecond. The simulator will order the events like 100, 200, 300 like that in the order. But suppose this AND gate is driving another OR gate, the AND gate output is driving another OR gate. Now because of change in the input of the AND gate 100 nanosecond, output changes maybe after say 101 nanosecond. Okay. So when the simulator computes, earlier simulator had say 3 events at the input of AND gate 100, 200 and 300. But when it simulates it finds that the output of the AND gate because of the 100 nanosecond change has changed at 103 nanosecond. So now it has to add an event between 100 and 200 at 103, then only the next OR gate behavior can be simulated properly. So that is what I mean, the events as it happens, like when the simulation happens maybe there are you give some inputs, some events and it is ordered properly, but the simulator as it simulates new events happen in the internal signal, that is pushed in at the appropriate place in the correct order, and one by one the input is taken and simulated. So that should be understood. The best thing is that you draw some 2 or 3 level circuit and imagine some input, and you try to compute and order it in the proper way, then you will understand it. It is better you yourself work it out. I could have shown a picture, maybe as we go along some pictures will be shown which is related, from there you can grasp. So that's the idea of simulation time. So don't get confused, and there is some the most textbook will talk about a simulation cycle. Basically it shows a resolving the concurrency by sequential computation, okay, and they will call describe something called delta delay. We will see that in a moment, okay. So let us move on, let us see how the simulator simulates the sequentially written code, or the concurrent behavior is simulated properly. So please have a look at the circuit which is shown here. So here we have a very simple circuit, an AND gate and a NOR gate, and AB is going to an AND gate and the output of the AND gate is X. X and C primary input is going to a NOR gate, which is output is a Y, and the AND gate has a delay of 3 nanosecond and the NOR gate has a delay of 5 nanosecond, and we know that the AND gate 1 1 is 1. For the NOR gate, if any input is 1 the output is 0 because it is opposite of OR gate. Now we have not learned about how to specify the delay in VHDL, but this is the way to specify it. We are writing the description, but we are not writing the statement, concurrent statement in the order of the data flow. Data is flowing from AB to X, X and C to Y, but we are going to write this part first and this part second. Say Y gets C NOR X after 5 nanosecond, that is this one, and this is the way to add a delay, the model the delay in VHDL only for simulation. Just like if you write a statement like after 5 nanosecond, definitely you are not going to get a NOR gate with 5 nanosecond delay. If you give it to a synthesis tool, it is going to generate some circuit like this, ignoring this is not going to give any delay, or it gives if you go to FPGA it will map to some circuit, whatever may be the delay of the circuit you get it, okay. There is this is not for synthesis, it is only for simulation, but if you simulate this circuit it will definitely show the output will come after 5 nanosecond delay, okay. Now X is A and B after 3 nanosecond. Now you see that the Y is written first and X is written after that. So the order of the statement is opposite to the order of the way the data is flowing. Now normally as in sequential language simulation, if the simulator looks at the, like if there is an event on A, it computes a Y first then X, then nothing is going to happen, because the Y say C NOR X after 5 nanosecond, whatever was the old value of X is used for Y computation, but X is computed and where the new value of A is used and X is correctly computed, Y is not correct, and you can imagine what happens if you have a 5 level circuit and everything is jumbled up, okay. So this is a little bit hopeless situation. We have to make, the simulator has to make some sense out of it, okay. Now we cannot say that you look at the order in which the data is flowing and rearrange the statements and so on. This won't work definitely because you can have a feedback, okay. So when like suppose you have something one more level and the output is going back to the input, then what is the order? When there is a feedback there is no order. It is like you go to a stadium where a running race is in the progress, okay. You go, people have running a say a long distance 10,000 meter running in a 400 meter track, and you go in the middle, and if you look and you might guess saying that somebody is in the front, maybe the you will imagine the tail ender is the top end like that, you know. So similar thing in a when you have a cycle, you cannot decide which is the first. So ordering it in a proper way is impossible. So but if you think it is very easy, because you know that the computation start because of an event. If an event happens on A, then the best thing to do is, instead of going from top to bottom, look at the right hand side of the assignment. Wherever there is A, you compute that. So that is a game, and there could be multiple statements with A, it does not matter. Suppose the simulation time is 100 nanosecond, at 100 nanosecond you compute X, and there may be an Z. With A you compute Z, really does not matter, okay. Whatever I am going to show you is a simple case, but that can be kind of interpolated to a more complex case, only you need to work it out, okay. So the rule of resolving concurrency is very simple. Look at the right hand side of the assignment, wherever there is an event, and compute that, okay. Now you take this simple case, let us assume that A is changing at 100 nanosecond. So suppose initially A was 1 1, the X is 1, so A is changing from 1 to 0. Then look at the simulator will look at the right hand side, there is an event on A, and you look at the right hand side here, there is nothing, so this need not be computed. So A changed at 100 nanosecond, so it will compute a new value of X, and it will assign at 100 plus 3 nanosecond, 103 nanosecond. The moment that happens, now some signal has changed. Now again the simulator will look where the X has changed at 103 nanosecond. So what the simulator does is that the current simulation time is 100 nanosecond, and there is a 100 nanosecond event, it has computed some signal, some assignment for 103 nanosecond. If nothing else need to be computed for 100 nanosecond, it will keep the event in order. So suppose the next event on X was 200 nanosecond. Now since there is a the A is 200 nanosecond, since there is an event on X at 103 nanosecond, it will look at the right hand, simulation time is forwarded to 103 nanosecond. It will look where X happens and compute the Y, and that will happen after 103 plus 5 nanosecond. Again it looks if there is anything remaining to be computed for 103 nanosecond, and proceed for the next simulation time 108 nanosecond, and so on, okay. That is how the simulator resolve the concurrency. It does not matter however many statements are there, whether there is feedback in whichever order, and instead of the AND gate there are very complex circuit, this game works, anything can be easily the concurrency is resolved by very simple method of looking at the right hand side of assignment where the event happens, that is computed, and new event happens, that is ordered properly, and it proceeds. So that is what is shown here. So we have at the time 0 A and B are 1, so X is 1, C is 0, so because of X 1 Y is 0. Now at the 100 nanosecond B remains there, A changes from 1 to 0. So the moment that happens, this A appears at the right hand side, X need to be computed. So X is assigned a value, because A is going from 1 to 0, X will go from 1 to 0, but that happens at 103 nanosecond, and Y remains same because at 103 the Y is there is no change in the X at this point at 100 nanosecond, so Y does not change. Now since there is nothing else here to compute at 100 nanosecond, the simulation time moves from 100 to 103, and there is an event now on X that will, you look at the right hand side, that will trigger a computation for Y, and that that is basically 0 nor 0, which is nothing but 1. So the y will change from 0 to 1, which is assigned at 103 plus 5 nanosecond 108 nanosecond. Since there is nothing remained to be computed at 103, the simulation times move to 108 nanosecond and everything is stabilized. So if you put a waveform, this comes very cleanly. So basically the game is about resolving the the concurrency. The issue is order of the statement will not match the data flow. The order may be different, and the solution is an event driven computation. And you look at the right hand side of assignment, and one after the other you compute, and that might trigger the further events, and you order them properly, and then you treat them one by one. Everything's worked properly. If you have any doubt, you can really I have definitely shown some very simple case. You can introduce, say like event on A at 100 nanosecond, at 110 nanosecond, 120 nanosecond. You can even think of a scenario where A is changing at 100 nanosecond and also at 102 nanosecond before even the X changes. Okay. So you think really what happens, you try to work out such a situation that will bring clarity to your thinking. And so this shows essentially what I have told is that how a simulator resolve the concurrency from the sequentially written statement. It is a very simple idea, it is not a very complicated idea, but the simulator may have to compute quite a lot of computation need to be done, but the idea is very simple. Whenever there is an event, look at the right hand side, compute those statements which is an event, assign the output, order the events sequentially properly, and then when every computation at the particular simulation time stabilizes, go to the next event, next simulation time, and keep computing. That is a basic idea. So with that I try to complete today's lecture. The second part of the lecture shown, we have discussed the simulation, how a SPICE simulation happens for analog circuit by kind of discretizing the signal at various intervals depending on the need of computation. But in digital circuit you don't need to kind of introduce intervals. Whenever there is a change in the inputs that need to be recomputed. So the events whenever that's an event driven simulation, and for sequential circuit basically you can do whenever on the cycle based simulation on the active clock edge, that will reduce the computation. And we have seen a simulation cycle, how a simulator resolve the concurrency in the case of timing simulation. Okay, we will in the next lecture we will see how that happens in a logic simulation where there is no delay. That will definitely bring more clarity to the game. So I stop here. Please go back and revise whatever is done, refer to the textbook to get hold of the terminology used, because I have avoided to explain the concept in a very simple and lucid way. So please revise, refer to the textbook. Thank you, and I wish you all the best.